In this session, we shall talk on three important converters. The push-pull converter, which I have written here. The second one is the half-bridge converter. And the third one is the full-bridge converter. These three converters are generally used for higher powers. In the order in which I told, push-pull converter, then followed by half-bridge converter, still higher power, followed by full-bridge converter, which is for still further higher powers. All very high power converters are generally the full-bridge converters. Now, these three converters are also buck-derived converters. Only thing is that it is special in the sense that they have a kind of an ORing mechanism where during the 1 minus DTS period also power can be delivered to the load. I will explain to that how this ORing mechanism comes into play. This is done by having a center tap on the secondary side. So all these three converters have secondary as center tapped. So let us discuss these three very important converters which are very, very popular and used in many applications. So let us now consider the push-pull converter. Let us begin by writing down the typical forward converter with demagnetizing winding. This is the forward converter primary. This is VI or VCC. This is the demagnetizing winding which we discussed. The diode which is used during the demagnetizing time, the demagnetizing diode, and then you have the secondary. The secondary, you have the secondary blocking diode, and then you have the secondary side, the freewheeling diode, where the inductor freewheels during the time when this BJT, primary side BJT is off. You have LC and the load are not connected in this fashion. So this is our typical forward converter. Let me place the dot polarities on the primary side. If I place the dot here, remember that the dot polarity is down below here for the demagnetizing winding, because we want this demagnetized winding to come during the time when this switch is off. The secondary side will have similar kind of a dot polarity like the primary, because we want the power to flow to the secondary at the time when the BJT is on. This is regular forward converter which we know, and we know how it operates. So let me put a diode here. This is actually not an extra component. Most of the switches, the MOSFETs, IGBTs, will have this internal body diode coming into the picture. So I have drawn this for the sake of completeness and also symmetry. Now this diode is there. Let me also make that into a controlled switch. So an IGBT, and this diode is actually the body diode of an IGBT. So imagine it in that fashion. So now you have two controlled switches. So let us play around placing of the switches to see how the push-pull converter evolves. Now the concept is that during the time when the BJT is on, the primary is energized and it will pump power to the secondary, and then so on by buck converter action to the load. And during the time when the switch is off, the flux in the core demagnetizes by a current flow through this diode, through this demagnetizing winding, and into the supply. Now instead of pumping this power into the supply, let us pump the power into another winding and then route it in some manner into the output. So then we can have this an output which is having a higher power than as compared to the one where this ORing effect doesn't come into picture. Now, how to bring about this ORing effect? Let us see that. And this demagnetizing winding in the forward converter is a very low power winding. It has very thin wires, and it can handle only the magnetizing current, cannot handle the power currents like the primary and the secondary. So that is one change that you have to do. You will have to change this demagnetizing winding into a power winding and then reposition it. So let us see how we can bring about using this demagnetizing as a power winding, and also try to steer the power through another winding into the output rather than putting the power back into the source. So let us first mark this. This is Q1, this is Q2, and this Q1, let me shift the position in this fashion without altering the circuit in any way. So this is, I am, instead of putting it down vertically down to ground here, I am going to place this transistor Q1 in this fashion horizontal and make space here. Okay, so next let me make space and let me bring the supply Vi again in a horizontal fashion like this here. Remove that, and now I have made space here. Now this winding, this demagnetizing winding, what was supposed to be demagnetizing winding, I'm going to flip and pull it up like this from this common point. So from this common point, first the non-dot end, and then after the non-dot end, the dot end will come at the remote side here. So from that you see this diode and transistor combination switch coming in here, the diode, and this is Q2, and I place the dot here. So now I can remove this winding and this part. Yes, so now it is that same forward converter transformer with the demagnetizing winding, but the windings placed in such a fashion that it now looks like the primary is a center tapped common winding. Both are on the same course, 1:1. Now let me, for routing power to the secondary, I will replace this with another winding here. I am center tapping the secondary, and the dot, I will place the dot here, and on the non-dot end a diode. So let me erase this. In the non-dot end diode, I am not going to use an extra diode. I will use the freewheeling diode and connect it to the non-dot end, and then I will make this connection. Now this would be the secondary side. All these windings, the secondary two windings center tap, primary two windings center tap, all will reside on the same core. So all this is one single core. Now this is called the push-pull transformer. Now this power supply, I can complete it and ground that one. So now we will call this, name the parts. This is Vi, this is V0 as we have normally named. V0 measured in this fashion. Then let us push it to one side because we need to draw some waveforms here to understand the operation of the circuit. Let us call this D1, let's call this D2, L, C, and this is I0. This is IQ1, and here current flowing in through this switch Q2 is IQ2. Okay, now to understand the operation of the circuit, let us draw the waveforms alongside here and get more insight into this operation. Okay, let me now draw a series of these lines. I will explain to you what these time divisions are. Now during this time, I will say this, during this time only Q1 is on. And I will leave this space. I will tell you what these other spaces are. Q2 is on only during this time. Q1 is on only during this time, and again Q2 is on only during this time. In all other times, Q1 and Q2 both are off. So during this time when I say Q1 is on, Q2 is off. During the time when I say Q2 is on, Q1 is off. But in all the other places where I have not written anything, it means both Q1 and Q2 are off. So that is the meaning of these things. Okay, now let me draw one axis, time, and this is the pole voltage Vp. And let us start by looking at the pole voltage Vp. Consider the period when Q1 is on, only Q1 is on. So when this BJT transistor Q1 is on, this is connected to the ground here. The dot end is connected to the plus of Vi. So Vi comes directly across this coil. So you are having plus minus across the coil like this. So because all the coils are coupled on the same core, you will see that all the dot ends are positive. Non-dot end is negative. On the secondary side also, dot end is positive. Non-dot end is negative. The other coil plus on the dot end, minus on the non-dot end. So let us see what is the voltage. The voltage measured in this fashion from non-dot end, keeping the common and the measuring probe on the dot end, you will measure Vi across this coil. And by induction, it is Vi across the other coil, even though Q2 is off by induction. In the secondary side, if you take a turns ratio of 1:n, you will have n times Vi. And the other coil also will have n times Vi. Now this will be the way the voltage will be appearing across each of the coils. Now Q1 is on, Q2 is off. There is no IQ2 current. Only IQ1 current is flowing. So the only active portion on the primary side is this, what I am showing through this cursor movement. So this coil of the primary is active, giving you a positive dot end positive Vi. On the secondary side, dot end positive, diode D1 is forward biased. The moment D1 is conducting, D2 is reverse biased, because you see that this is positive and the other end of the D2 is negative. That is reverse bias out of the picture. So only this coil, the top portion of the center tap secondary, is active because D1 is forward biased, D2 out of the picture. So D1 forward bias will charge up the inductor and this portion will act like a regular buck converter. So what is the voltage at Vp? NVi will appear at Vp with respect to the center tap. So it will be NVi. Likewise, whenever Q1 is on, you will have the same voltage appearing NVi here. So now consider the situation when Q1 is off, only Q2 is on. Only Q2 is on. So let us write down when Q2 is on, the dot end is now connected through Q2 to ground. Dot end is ground. Non-dot end is positive, Vi. Likewise, non-dot end of the other coil is plus, dot end minus. On the secondary side, non-dot end plus, dot end minus, non-dot end plus, dot end minus. And the voltages that you would see measured in the same direction, the minus Vi on the primary side across each of the coils. And on the secondary side, n times minus NVi and minus NVi. And now you see that D2 is forward biased, D2 is forward biased, D1 is reverse biased. So there will be a current flow through D2, through the inductor it will charge up, and there will be buck converter operation with respect to this portion of the coil. So you will see that this is the active coil. On the secondary side, this is the active coil. There will be power transfer in through this coil to the output. So on at the pole, you will see when Q2 is on, you will have plus coming in here Vp NVI. So I have NVI, and it will repeat for all Q2 on periods. So if I draw this in this fashion, complete the waveform, this is how Vp will look like. Why do we say it is 0? Why do we say Vp is 0 during the time when Q1 and Q2 both are off? So during that time, you will see that the inductor is freewheeling. The freewheeling path will go through like that. Look at the cursor, it reaches the center tap, and then at the center tap it equally divides into this path and this path, and back again through the diode, ORs up at this point and comes. So because the current is going one entering the non-dot end, the same equal current entering the dot end, in the core they are all coupled. One is having Ni MMF in one direction, in the other Ni MMF in the opposite direction, equal and opposite because the currents are getting divided by 2 exactly. So the MMF in the core cancels, there is no induction, the voltage across the coil is 0, therefore potential at Vp, both the diodes are conducting, potential at Vp is 0. Therefore I have indicated it as 0 here. Let us now discuss how the inductor current waveform looks like. Let me mark the inductor current waveform here, IL, and let us draw its waveform. This is the time axis, and let me mark this, label this as IL. Now let us take this interval when we say that Q1 is on. So when Q1 is on, we saw that this winding was active. This winding was active on the secondary side. D1 is conducting, Vp is at NVI, and we have marked that here in the Vp waveform. So what is appearing across the inductance, on one side you have Vp which is at NVI, on the other side you have V0, voltage across the inductor is NVI minus V0, and at the rate of NVI minus V0 by L, you will have a current rise because V0 is lesser than NVI. You have a current rise, inductance is charging, inductor is charging. Let me mark the slope NVI minus V0 by L. Now during this period, both Q1 and Q2 are off. So when both Q1 and Q2 are off, inductor current is freewheeling. It freewheels, passes through capacitance, and the load goes through this line through the center tap, and at the center tap it divides equally into two halves, one going in this direction, the other going in this direction. They are up at the pole point and then go through the inductor. So because exactly half the current is flowing through one part of the coil which is going through the non-dot end, and another part of the coil which is the dot end, the MMFs, Ni's, cancel each other, and the flux remains at wherever it was, and there is no d phi by dt. As a consequence, there is no voltage induced across any of the coils, and therefore Vp is 0, and we have indicated Vp is 0. But there is V0 on the other end of the inductor coil, and therefore the voltage across the inductor is minus V0. So it will have a falling slope of minus V0 by L. And then during this period Q2 is on, and when Q2 is on, this coil is active, and on the secondary side this coil is active, D2 is active, Vp we saw is again NVI. So consequence, inductance will charge up again at NVI minus V0 by L rate, then it will fall down at minus V0 by L, and this repeats. So if you take the average of this, draw an average right through, this is the DC part, and this DC part is nothing but I0. The reason is that I0 is the part that is going through the load, and it is the average part. The part that is going through the capacitance is the zero average part. There is no average current through C, and therefore the entire average has to go through the output load, and therefore we have indicated it as I naught. To get a better insight into the operation of the push-pull converter, we need to look at the flux within the core. How does it look like? So let us deduce the waveform of the flux within the core. You cannot see the flux waveform on the oscilloscope, but let us deduce it using the Faraday's law. So let us draw an axis, time axis t, and we would like to draw the waveform of the flux within the core. Now let us say during this period when Q1 is supposed to be on. When Q1 is supposed to be on, this point is grounded. This point of the coil is grounded. The dot end is connected to Vi. So the dot end is more positive with respect to the non-dot end. So therefore, you can expect the flux to increase. You have the positive MMF being applied, flux will increase. So in this period, the flux will go from minus to plus, from minus 5M to plus 5M at a rate. What rate? It will go at the rate of this voltage, whatever the voltage which is being applied, divided by that number of turns of that particular winding. So if I take the primary winding, half from the center tap to this end, the voltage across this coil is Vi. Let us say Np is the number of turns, then Vi by Np is the rate at which it will rise. If I take the secondary winding, Ns is the number of turns, and the voltage across the secondary winding is Nvi, and therefore the rate at which the flux will change is Nvi by Ns. But because Ns is related to N, you will see that both these rates are same. So let me write that down. This will be the way the flux will change, constant rate, voltage divided by N, because we are using V is equal to N d phi by dt. This is the d phi by dt rate. Now importantly, during this time, this period when Q1 and Q2 both are off, when both Q1 and Q2 are off, I said that the current, inductor current, is freewheeling. How does it freewheel? It goes in this path. This path I have just shown as a short path, but actually it will go through the capacitance and it will also go through the load and then or up at this point. So I'm just indicating it that it goes through these two impedances, then it comes in this direction, and then it splits here equally, exactly half, because these windings are exactly equal. So whatever the inductor current, IL by 2 will go there, IL by 2 will go in this direction, and then you have IL by 2 coming from this diode D1 and D2 also IL by 2. Both these will OR up and then flow through the inductor again. But importantly, if you take this part here, IL by 2 flowing into the dot in the lower half of the secondary center tap winding, and here IL by 2 flowing into the non-dot end part into the upper half of the center tap winding. So the upper half of the bar and the bottom half, they are having opposing MMFs, and the MMFs cancel. There is no magnetomotive potential, and therefore flux wherever it is will not change. It will remain. So the flux was here and it will remain at that point. So if it remains at that point, what is d phi by dt during this period? D phi by dt is 0. There is no slope. So if d phi by dt is 0, all the coils coupled to the core, the primary top, primary bottom, secondary top, secondary bottom, all will see 0 voltage, because d phi by dt is 0. And because these voltages are 0, Vp will also be 0. So therefore you see the voltage of Vp 0. Next, during Q2 on, when the Q2 is on, dot end is negative, non-dot end is positive, and therefore you have a negative magnetomotive force and it will start falling like this. And then during this period, both Q1 and Q2 are off, flux wherever it is will stay. So it will stay there. And then from there again it has a positive rise, Q1 on, stays, and then Q2 negative rate falls and stays, so on. So you will have this plus phi m, this is minus phi m. You will see the flux swinging from minus phi m to plus phi m, and in between, when both the switches are off, the flux just remains. d phi by dt is 0, and voltages across all the coils are connected. All the coils on the same core will be 0. Let us now look at two other important waveforms in the push-pull topology. One is the current that is flowing through D1, and the other one is the current that is flowing through D2. These two currents are pretty unique in shape. You would not have seen this current waveforms, this type of current waveforms in other buck derived converters like the forward converter and the non-isolated buck converter. In the push-pull, half bridge and full bridge, you will see this type of currents flowing through the diodes. So let us have a look at them. Let us draw the t-axis and look at the ID1 current here, and another axis, another t-axis, and let us look at the ID2 current here. Let us first draw the level, because it is the inductor current that has to flow through ID1 and ID2, parts of the inductor current. We will see which part of the inductor currents will flow through, but first let us mark this average level of the inductor current, which is I0, like that, and for ID2 also I will mark the level. Now when I take ID1, when is ID1 active? Whenever Q1 is on, this winding on the primary side is active, dot end. Whenever the dot end is positive, you have the dot end positive, and this portion of the winding, top half of the secondary will be active, and D1 will be active during that time when Q1 is on. So it will just follow the inductor current. Whatever the inductor current was will be ID1 during that time, and we can write that down. And you see Q1 is on again here also it would be the same thing. Now what is happening during the time when both Q1 and Q2 are off? Here also Q1, Q2 off, here also Q1, Q2 off, here, so on. Now during the time when both Q1 and Q2 are off, the inductor current is freewheeling, and we see that at the center tap point it is dividing into exactly two halves, IL by 2 and IL by 2 through D2. So D1 will be carrying IL by 2 during the period when Q1 and Q2 are off. So this is the IL waveform. By 2, half of that will flow through ID1. So like this, half of that. You see that it is having a downslope, negative rate. So full wave, the IL waveform would have been like that, but half of that would be like this. So like that we can draw there also, and the other side here also you see that it is both Q1 and Q2 are off. The inductor current divides exactly into half, and that is how it would look. So this is the type of waveform that you would see for the D1 current. And for the D2 current, also similar. During Q2 you will see that the D2 is active during the time when Q2 is on. So D2 is active, and you will see during this time it is exactly the same as the inductor current. During this time also it is exactly same as the inductor current, and during the time when both the switches are off, half of the inductor current, so half is flowing through ID1, half is flowing through ID2, and here also you see that half flowing through ID1, half flowing through ID2, likewise here also. So completing the wave shape, you will see that, so during this time only ID1 is flowing, ID2 is 0. During this time only ID2 is flowing, ID1 is 0. So you will see that the diode currents on the secondary side will be like this, and if you actually probe the currents in an actual circuit with the help of an oscilloscope, you will be able to see currents like this. Let me remove the waveform ID2 and make some space, and in this space I will include another waveform, another very important waveform, the voltage across the switch. The voltage across the switch Q1 and Q2 are very important. We'll be discussing that now. The voltage across both these switches are very similar, except that they are phase shifted. I will look at only one of the voltage waveforms across the switch, either Q1 or Q2. I will take Q1 for now, and let me mark the way I am going to measure in this fashion. VCE1 is the label, and let us bring that label down here and see, look at the waveform here of VCE1 across switch Q1. We know that when the switch Q1 is on during these periods and during this period, the voltage across the switch Q1 VCE1 will be 0, almost 0, and we will put that down. Now the another state is when Q2 is on. So when Q2 is on, Q1 is off. When Q2 is on, this dot end here is at ground potential, and this point here at the non-dot end. See that each coil is having VI with the positive side on the non-dot end, VI here also positive side on the non-dot end. So overall, from this point to this point, you have two VI coming across the switch. So therefore, when the switch Q1 is off and Q2 is on, these two periods here, we'll see 2 times VI coming across the switch Q1 because of the voltage induced across both these coils. Now during the time when both Q1 and Q2 are off, we saw that the inductor current is freewheeling in the secondary side, and the inductor current is splitting into two equal halves, and you have opposing MMFs Ni on one side in the top due to the current flowing in the top half of the secondary center tap into the non-dot end, and due to another equal and opposite current flowing into the dot end of the bottom half of the secondary center half, causing MMF cancellation and no flux, and therefore the voltage across all the coils is 0, as we see here, even across VP, and therefore if this voltage is 0, this center tap point, which is at VI, will come directly to the collector point of Q1, and therefore they will all be at VI in between this. So this VI, this is the voltage waveform that you can expect to see on the oscilloscope across the switch Q1 VCE1. Similarly, you would see across the switch Q2 VCE2. Only thing is phase shifted, with the zeros are the low voltage, almost zero voltage occurring during this period, Q2 period. So now let us try to calculate the voltage equation, input-output relationship. First, let us see what is the time period. Now you see that this is the time when the switch Q1 is turning on, and it's on for this period. I'll call that one as DTS. This whole period is TS till again the cycle repeats. And this period when the switch Q1 is on, we call that one as DTS, as the duty cycle of the switch Q1. Likewise, the duty cycle of switch Q2 also is DTS, only it is turning on here during this period. So now this is the switching pattern for the devices. But what is the what is the duty cycle for the voltage profile at VP? You see that the voltage profile at VP is slightly different in the sense that it is having double pulse in that same TS period. So VP is actually having double the frequency as compared to the switching frequency of these two devices. So therefore, this 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 arrow or dimensioning that I've indicated here will be the frequency of Vp, and this time is Ts by 2. So therefore, what is the duty cycle for Vp? The Vp duty cycle will be this period, which is dTs, we know it's dTs, divided by Ts by 2. So this is nothing but 2 times d. So the duty cycle for the Vp or the pole voltage waveform is 2 times the switching duty cycle of the individual switches of the push-pull converter. So therefore V0 here is nothing but Vp into the duty cycle, and duty cycle is 2d. And Vp we know is N times Vi. We have marked it here. We saw how that came about. Therefore, we can use NVI for Vp into 2d. So if you write it down here, 2 to N into Vi into d. D here is the switching duty cycle of the independent switches. This is the input-output relationship for the push-pull converter.